So, welcome back to the second lecture in this series of lectures on the moving charges and magnetism. Okay. Now, after having done with the Lorentz force, okay, where we had the magnetic field and electric field working together and putting a force and getting the BIL sine theta, okay. In fact, it is I L cross B, so ILB sine of theta, but my teacher told me call it Bill sine theta, okay, and I remembered it for a long time as Bill sine theta is the force which works on a current carrying conductor. Now friends, we are going to talk about a little bit of a different aspect, and let's go back, revisit mechanics. In mechanics we talked about a work done when there is a force and the force has a component in the direction of motion of the particle, the mass. So we could write a dot product f dot dx, which is f dx cos of theta, and it is equal to the work done w. Okay, and this is finite only when this f has a component along or opposite to the direction of motion of the particle. Okay, so let us see as to what happens in the case of motion of a charged particle, charge q mass m, in a magnetic field. Okay, we find that the magnetic force is perpendicular to the velocity vector. Why? Because Fm is equal to qv cross b. So this Fm is perpendicular to both b and v and b. Okay, has to be. So it is perpendicular to the plane containing v and b. Just like what I said in the case of cross product, that a vector A cross vector B is equal to a new vector C. C dot B, C dot A, they are equal to 0 because there is a 90 degrees angle between them. And I explained it very explicitly. So I understand that if you have any problem, do revisit the vector dot and cross products. Okay. So in this case, there is no work done because both of them are perpendicular to each other. There is no change in the velocity, the magnitude of the velocity. That means the for a mass m, the kinetic energy half mv square remains unchanged. Okay, then what happens? So what happens but is that the direction of v changes. So the direction of the momentum also changes. Okay. So, but the magnitude of the half mv square does not change at all. Now let us contrast this situation with the situation of QE is equal to FE. That is the force due to the electric field on a charge Q. Okay. This may have a component. This force may have a component along or opposite to the velocity vector, and therefore there will be a change in the value of the magnitude of the velocity, and work has to be done in that case. Okay. Now, actually what happens, I've just shown that there is a uniform magnetic field going into the board. Okay, so I must have shown these crosses all along equally spaced like that, but because I'm drawing on a whiteboard, so I'm just taking the advantage and telling you that the magnetic field is into the board, into the board, into the board, etc. And away from this point O, there is a circular motion. What kind of circular motion is that? This is called UCM, uniform circular motion. On the charge q with the mass m, there is a velocity vector which is like this, and as a result, because the magnetic field is uniform, and I can show you with my right hand, this charge is positive. So for positive charges I use my right hand, or for negative charges I use my left hand, and my fingers, these 4 fingers, they will be in the direction of the uniform magnetic field, okay, and this is the direction. My thumb gives the direction of the motion of the charged particle, and then the pushing direction of my palm, that is this direction, will give you the direction of the force. So this is open palm rule which I subscribe to. It is not like the rule that we come across which is called left hand rule. It's one, the same result is obtained, but if you remember, but you must be able to say which is right and which is left hand. Okay, there is a story. Let me let us have some humor. Okay, so there was a new recruit in the armed forces. Recruits are called rung routes, rung route. Okay. Now this man had a very nice physique. Okay, he was very strong bodily and little bit weak mentally. So he was a fit case for being a sepoy. Now he was he was given to a subedar to tell him how to make the drills. So in the drills you have, if you have gone for NCC etc., you must have seen that your instructor says left, right, left, right, left, right, and you go like that, left and right. But this man couldn't say left, right, couldn't understand left, right. Then he tried ulta, seedha, no. Khabbe sajje, no. He was in military exercises. I have been a member of the NCC, so if I make a mistake, my instructor will say, take this gun and go for a fatigue, 1 round, 2 round, 3 round, like this, and I will run there. And all my colleagues, they will be subjected to that kind of a exercise, okay, although it may be a torture. Anyway, so one day, the instructor was very sad, and he was sitting in the canteen, and then his senior, the one who gave him instructions in the beginning when he was recruited, he was there, and he said, "What happened, man? What's the problem?" He said, "Sir, there is a new rung route and he is not following my instructions." So what's his name? His name is Ballam Singh. Okay. So he said, there is no problem. Bring Ballam Singh. Give him something to eat or drink. And the 3 of them, they went to the fields where the exercises were made. And what he did was that he put green grass and tied that green grass in his left foot and dry grass in the right foot. and this is called ghas and this is called phus. Then he made the instructions. Ballam Singh, see the nazar, see the kamar, ghas phus, and he will do the left right like that. So you must know what is left and what is right. So when you are using this rule, my palm rule, for left palms, open palms for the negative charges, and right palm for the positive charges. Left palm and right palm. So in this case you can see that I've got a positive charge. I have the uniform magnetic field going into the board. So all my fingers are going like that. You can also make your fingers go into the page of your copy, and then my thumb is like this. Then my pushing direction of the palm. Pushing direction of the palm, that is towards the center. Okay. So I can see that there is a center seeking force, a centripetal force towards the and therefore there is an acceleration, centripetal acceleration, and centripetal acceleration here also towards the center of it. And if you look, then what is there? This force F is the magnetic force, the force due to the magnet. Okay, I can write this as FB and FP respectively. Okay. Now this FB is equal to QVB sine of pi by 2. Sine of pi by 2, because V and B, they are perpendicular to each other. V is like this and B is into it. Okay. The two of them are perpendicular to each other. Okay. So sine of pi by 2 is equal to 1. So this becomes equal to QVB, and this provides what is known as mv square upon r. So now the mathematics is simple, very simple. Mv square upon r is equal to QVB, which gives me V and V will cancel, mv upon r, that is the P momentum upon r, this is equal to QB. Now we know that in circular motion, if equal angles are traveled in equal intervals of time, then V is equal to omega into r. So omega becomes equal to V upon r. Okay. So this turns out to be equal to V upon r will become equal to QB upon m. Okay. Now this Q by m is a very important thing for all charges, very specific to all charges. So sometimes this Q upon m is called specific charge of an electron, of a proton, of this, of that, etc. Okay. So this omega is now dependent upon the value of B. Okay. And you know that the frequency is equal to omega upon 2 pi. So this becomes equal to QB, okay, upon 2 pi m, right? So it gives, look here, it gives capital T is equal to 2 pi upon Q by m into B. 2 pi Q by m by B. Now this is a constant, and for a given magnetic field, the time period is the same. So it is independent of the radius over here. So the magnetic field is there, the Q by m is there, and then we get the time period. If this r is more, doesn't matter, the time taken is the same. And this becomes one of the things which occurred to those people who made the cyclotron, to use this very property to confine the long 3 miles, 5 mile long accelerators into a accelerator which could be accommodated in a room like this. Okay, this is one thing. The other thing is now, which appears, there is a diagram which appears on the left hand side of your board. This diagram shows that the path is helical. The helical path is there, okay, and between two adjacent helix there is a pitch. This is when the velocity has a component in the direction of the magnetic field, okay. So when both of them are in the same direction, there is no force, but there is a velocity, and that means this circular path, this will go like this. It is like a helix. I will not be able to make that convincingly, so I am just putting on the left hand side a diagram, schematic diagram of a helical path of a particle in a magnetic field, where it has a velocity component along the direction of B. Okay. So next item that I am going to take here is the motion of a charged particle of mass for charge Q and mass M in presence of electric and magnetic fields. And that is, first of all, we are going to talk about the velocity selector. In the next lecture exclusively I will talk about the cyclotron facility. That also uses the same kind of mathematics. So here I have just taken my charge here, okay, Qm, and this is the x-axis, this is the y-axis, and this is the z-axis or the z-axis with the unit vectors I, j and k, which I have shown over here, and along the x-axis we have the velocity vector, along the y-axis we have the electric field, you can see here parallel to the y-axis, and the magnetic field in the direction z, and that is, it is coming out of the board. Okay, I can show it to you that with the left hand, that this is the x-axis, this is the y-axis, and this is the z-axis. Okay, so with that I write the net force because of the electric and the magnetic fields together, that is QE plus B cross B is equal to FE plus FB. This is exactly what the Lorentz force is. Now I can write the electric field as equal to the magnitude into the j cap, and the velocity vector as the magnitude v into I cap, and the b vector as magnitude b into k cap. Okay. Now if you remember, then I cross j is equal to k, j cross k is equal to I cap, plus k cross I is equal to j cap. So this is in the cyclic order. If I just say that I have I cap, j cap and k cap, and if I go for the cross product, this to cross this, I will get this, and this cross this, I will get this, and this cross this, I will get this. Okay, so this is one cyclic order that I told you about. And of course, because A cross B is equal to minus B cross A in the vector cross product, so if I j cross I will be equal to minus k, k cross j will be equal to minus I, and k cross I will be equal to minus j. We are going to use this one. Okay, so let me write the value of Fe, QE into j cap, FB is equal to Q B cross B, and I can write the magnitudes VB, QB cross B, I cross K, and that turns out to be equal to minus J, this one, and so it becomes equal to minus Q VB J cap. Now if the total force, net force because of this plus this is equal to 0, so I can write this as Fe plus Fb and QE minus QVB J cap. Okay, this gives us QE is equal to QVB, and Q will cancel out, and we get a formula V is equal to E by B. Okay, so if the arrangement is such, then only those particles Qm, okay, with velocities given by E by B will follow this thing and will pass in a straight path, which is required for a mass spectrometer. Okay, and there we can also say to isotopes and this and that. So this is the formula for selection of a particular velocity. All other velocities, they will either the particle will go like this or particle will go like this, and if there is a hole through which the particle has to pass, only those particles will pass whichever velocity given by E upon P. Okay. Velocities are normally very high, so that the magnitude of E numerically will be much more than the magnitude of P, because the velocities are several hundred, even thousands of meters per second. Because what actually is there in a mass spectrometer, that we ionize the atoms of particular kind and using an atomizer, and then they are accelerated by electric fields, and then this velocity is selected for further action. So this is it for the day. I wind up here, and thus we have seen that the moving charges in the magnetic field, okay, they are subjected to this kind of thing, and the velocity selection is done by means of this thing. So it has been a pleasure today to talk to you about this subject, and tomorrow exclusively I'll talk to you about cyclotron and some problems based on the set of equations and set of principles that we have learned in the last two lectures. Thank you very much. See you again.